The following content has been provided by RWTH Aachen University.
Hello everyone. Welcome to the Lab of Designing Interactive Systems 1, or Studio, how we call it nowadays. This will be a lot more interactive than the actual lecture. I hope you all still have these exercise sheets that we put online with Fitz law and maybe some other things that we send you. Maybe Ollie, you can put the link again in the chat. And we will also have a link to a Google spreadsheet that we will have later. So Ollie will probably put these in the chat. And I hope we can all do this together. This is the first time that we're doing this online, so this will be fun. Also, this is the first time for me that I'm actually presenting on an iPad, so I hope everything works out. If there will be some technical issues, please bear with me. We'll try our best that this is as close as possible to what you would have during a course where we actually meet each other and see each other. And something that I have to ask you is, it would be nice if you have like a nickname here in Zoom, if you make it something that's actually close to a name. I saw some weird things in there, and I don't mind your privacy at all, so you don't need to put your actual name in there. You can name yourself whatever you like, but please make it as something at least close to an actual name. So also not fantasy names, please. I don't want to call out Darth Vader to come up and show his exercise or something like this. Again, it's just easier for me to call you by something that resembles a name, but it doesn't have to be your actual name if you're not comfortable with sharing your name here. Again, as with the lecture, we are recording this because there's also some part of the lecture here which we were not able to cover. So it's the same if you ask a question, if you speak with me, your name will, your voice will be in the recording and your name that I call out then, but not your video or anything else. If you're uncomfortable with this, just tell us and we might also delete your voice later or something like this. Another thing is we actually found out that the online management lecture, whatever thingy, distributed the wrong time slot to us. The lecture is supposed to be half an hour longer than it was right now. So the time slot that we will have will be half an hour longer. If this collides with any courses or any other courses, we're terribly sorry for that. We cannot change this, but therefore we will record the lectures and you can look at the recording afterwards if you have a strong clash in there. So yeah, we'll try our best to have the recordings up as soon as possible then. Okay, also I will now look down to see my iPad and present on my iPad, so I don't immediately see the chat all the time. So if you want to get my attention immediately, you can just speak up. I don't mind if you do that. Interrupt me. You can also call me just by my first name. Just say, hey Marcel, I have a question. And then I will try to answer your question as fast as possible, but Oliver will have a look at the chat. He can also interrupt me. I will maybe sometimes look at the chat. And so let's try to start this thing and see how this will turn out. Okay, so the thing that we will start first is something that's called Fitz law. And it's actually a model that tries to somehow, model human behavior with an actual formula. Actually, it's quite fun to derive this formula by an exercise that we will do first. So this is where you should have your sheet. Your sheet should have something on there that kind of resembles what I have here. And I will also try to do this actually with you together. So you can see me doing it and you can have the same with, for you. So I will try to open the sheet on my side now. Let's see how this works out. There's the experiment sheet. It should look like this for you. And then you go to this experiment 4 thingy here. And what I need you to do now is here I need my friendly assistant Oliver later, because he will need to give a timer for this. And what you need to have is a pen in your hand. You need to have this sheet that I also have in front of me, in front of you. And we will do dots into this sheet. So you can see I can scribble on there. And what we'll do now is you take your pen, hold it over the left part here, over this part. And then we try to make dots in between these lines here, so in between these two lines and these two lines, and you basically alternate back and forth between the two. So you're doing something like tap, 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 tap. I hope if you saw this there. And you try to do this as fast as possible within 10 seconds. And we'll do this for all these thingies in here. So let's get onto it. So I will have, let me quickly erase what I have here. And I will have Ollie call out the timer. And then I will do this with you and instruct you on any further things that you need to do. But first thing is we need to do the tap, 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 tap on the slide now. So Ollie, you can give it a go.
Be fast, and we start when I say start, and it is start. Stop.
Okay.
Oh.
Yes.
Now, this, you will first of all do everything on paper, right?
Yes.
Okay, then we can just continue.
Yeah, and also what we will do now, let's do this once for here. We will do all the otherwise consecutively afterwards, but I will explain you what you have to do so you can keep an eye on this. So afterwards, we are going to count just on the left side, just on this side, how many times you tapped into these thingies here. So into the center of this here. And you also only count these that are actually inside of the two lines. So you, for example, I wouldn't count this one here. So let's do this for me then. So I have 1, 2, 3, 4. Let's say this one, 5, 6, 7, 8, 9, 10, 11, 12. So I have roughly 12 taps in here. So I note that down here. We'll later note it down otherwise. So this is what we will do now for all the other things. So let's do it first for all of them, and then we will count them. Okay. So you should have your sheet ready again. I'll do that. Actually, that is correct. I think it was before. So, okay, Ollie, you can do it again.
Yeah. So start.
It's good, but let's just say it's an experimental difference or something like this. Okay, then what you need to do next is go always here to the left side and always count these that are inside these two lines here. So let's do this for me. So, and if you want to, you can put them basically up here into this table. So for me, it was 12, 9, 8, then where am I? 12 again, 12 and 10. And the last one was 21, 16, 12. 21, 16, 12. So I will give you some seconds to put that in there. Okay. And the next thing then that I'm asking you to do is to open the spreadsheet where Ollie posted the link to in the chat, and basically put these numbers that you have in here into the spreadsheet. It should roughly, I hope I have it open. Yeah, it should look like this here. And then I'm also going to do this for me. I'm adding my numbers to this. Do this on my computer. Okay, I already see some numbers in there. Yes?
I don't know where your numbers are, but I see many students entering.
Great. I put my numbers in now. No, it took the first row. I'm taking the first row. 12, 9, 8. Oh boy, the performance of the thing is struggling. 12, 12. There it is. Nice. Okay. So let's go back, or let's put your attention back to me and what I'm going to present you there. So the interesting part that we are going to look now is this part below here. And there we can basically see, so first of all, you can also see, if you're interested in this, this here always where your average times, of how many times you tapped into the left thingies. And as you can see, the numbers are decreasing. Then what we're doing, we can also see the standard deviation here, the median of all of this. And then since we will be interested in a sort of time in there, which time we're going to reveal now, we basically divide the median, or we divide 10 seconds. So the 10 seconds that we gave you by the median. So we want to see of basically how many times you were able to do this in this 10 seconds. So, and the interesting thing is now this here. So this is basically the time that you needed to go from one of the thingies to the next thingy. So over the whole distance between the 2 lines on the left to the 2 lines on the right. This is what the numbers in here mean. So, and this is also the time that we are interested in, that we are going to predict. So basically what we did, let me roughly do a sketch for you so that you understand what we did. We gave you something like this here. Let's say you have something like a mouse pointer. And we want to know how long it takes you to go from here, from your mouse pointer, to the center of this button here. And this is the time we are interested in. So the time it takes you to go with your mouse pointer to this position here. So, and let's see how you performed and whether we can derive a formula from this. So what we see here is the distance between the targets. So we had 4 centimeter, 8 centimeter, and 16 centimeter. And what we have on the top here, so on this corner, there will be a lot of errors afterwards, I realize. We have the width of the target that you were going to hit. So this here, let's call this D, was the distance that I have on my sketch here. And this on the top here, let's call it W, the width of is was the width of the target that you were trying to hit. W. So, okay, so let's look at these numbers. So what we can see here is from here to here, we increased the width of the target. And what we can see is the time it took you to hit the target actually decreased. So going from here to here, you can see first you had 0.8 seconds, 0.7 seconds, and then roughly 0.6 seconds. So what we can say now is that the time it takes you to hit your target is kind of anti-proportional to the width of the target. And then what you can also see is that by increasing the distance of the target, so from going from 4 to 8 to 16, actually the time increases. So we first have 0.8, then we have 1.1, and then we have 1.2. So what we can also say is that the time is apparently also proportional to the distance. So there seems to be a relationship between these. So let's try to also start to get to our formula. So we want to have the position somehow, and we now already know that it's anti-proportional to the width and proportional to the distance. So we have the distance divided by the width to get there. And now what we can see, or what we can see if you look at this graph here, that apparently, and also if we look at the numbers, apparently it's not really linear what we have in there. So what you can see, for example, let's keep the width constant. So let's look at the 0.5. We are always doubling the distance. So first we have a 4, then we have an 8, then we have a 16. So we double the distance. And we might expect that then the time it takes you to go from one point to the other would also double. But if you can look at this number, we have 0.8, 1.1, and 1.25. The time does not double. And as you can also see here on the graph, yeah, also not a linear graph. So do you have something that you think what this relationship is when it's not linear? Let's try the first question. You can raise your hand in the participants thingy. You can also write it in the chat. I would love to also hear your voices. Sometimes you can also write it in the chat. But it's also always a little bit weird to just see the chat. So I would be glad if at some point in here, somebody of you actually gets out of their comfort zone, raises their hand and tries to speak with me. But yeah, people already wrote in the chat, it's a logarithmic relationship. Yes, so we put the logarithm behind, around this. And then we already roughly have this relationship that we are looking for. And it's very close at the actual relationship. So this what we have down here is something that's called Fitz law. So you write it like this. You write it with 2T? Yes, right? I think yes. So it's the law by someone called Fitz. And he actually found this out very early. I think it was around 50s or something like this. And then what he actually did, I think he did it with cockpits of jet fighters in there, and he tried to see how long it takes a person to hit a button. And he tried to then optimize this by actually moving the things around, maybe making the buttons larger or decreasing the distance that you have to hit the button. Because yeah, when you're in the cockpit of a jet and things happen, you need to be able to react pretty fast. Let's say your cockpit is burning and you want to eject fast. Yeah, Hannah, I see a question by you.
Yeah, I wanted to ask if there wouldn't be also a training effect, because I felt like it was easier to do the exercise after some time.
Yes, right. There obviously is. There is a training effect, which I kind of discarded in here. But yes, usually what we could have done, I think we also did it in the past, and I just missed it here, that some people start at the bottom and some at the top, and some people start at the bottom. And we try to kind of counteract this effect by this. Yes, of course, there is an effect that you learn how to do this. And therefore, we're always saying that Fitz law kind of tries to guess the average how a human would perform in this, and not like actually precisely predict the number in there. Also what Fitz found out, because this he also derived this formula experimentally. So he basically took humans, let them press a button several times, and then he always tracked the time they took them to press this button, and he put this in a sheet and then saw how it fits. And then he also found out that apparently the distance, that apparently it's not just the distance divided by the width, but it's also, yeah, this was the same wrong thing, sorry. Distance, go back here. It's 2 times the distance divided by width. And also he found out that that this fits best if we have the logarithm of it with a base of 2 in there. So, and that's the actual original Fitz law formula where we have the logarithm of the base of 2 of 2 times the distance divided by the width. And that's Fitz law. And this gives you a calculation where you can go to an interface, see how is the width of a button and how is the distance from, let's for example, say your cursor to this button, and then somehow estimate how long it will take a user to click this button based on these numbers. So let's go back to the slides here. Okay, so here we have this again. So what we saw here is that doubling the distance adds roughly a constant to execution time, which indicates the logarithmic nature that we saw. Doubling the target width gives about the same results as halving the distance, which indicates that we have a connection of d divided by w in this formula. So we were kind of good with this. Okay, then let's say again, so what is Fitz law actually? So here I have this example of a button that has to be hit, and let's say user does this a lot of times. So what you can also see that sometimes they overshoot here and sometimes they try to hit this button. So what basically happens in your mind in there is that you try to approach this button, then your mind kind of tries to slow down beforehand. This is why the width actually is good for you. So a larger target is better for you. And the distances, of course, it takes you some time to go the distance there. So let's see there. So as I said, the goal is to predict the time to press buttons, physical or on screen, as a function of distance and size. And then we have this Fitz law here. And he wrote then that the time to reach the position is something that is an index of movements times the index of difficulty. And the index of difficulty, one you can see, is basically what we derived ourselves here. So it's the logarithm of 2 from 2d divided by the width. And what he also saw is somehow if you multiply this by a time, which is 100 milliseconds, you kind of get the correct numbers in there. And he called, since it's to the base of 2, he called this kind of bits. So you're thinking of how you think about this index of difficulty. So what kind of happens in your head is decision making and close to what a computer would do. And he called it that this has basically bits as an indicator here. So it's 100 milliseconds divided by bits times the logarithm to the base of 2 of 2 times the distance divided by the width. Okay. And what you can also do is you can actually look at the CMN model, which we had in the lecture, and you can also derive Fitz law from this, but we won't do that here in the lecture yet. Okay, and you can also see that if we take this index of difficulty and put it on a scale like this, and then you can see there's also this linear increase, which suggests us that the logarithm that we took here is correct. Okay, so then let's look at the width of the target, because this is something that in the exercises and everything, you actually need to figure out correctly. So let's try the thing where we try to talk with each other again. Would you say that this button that you see here, or let's say this button, always has the same width? Or is it dependent from something? So if I come from here and try to hit this button, does it always have the same width? If you absolutely don't want to talk, you can also type it in the chat. Yes, Fabian. Yeah, you're sorry. I'm sorry you're muted still. So I cannot hear you. Yeah, I see you talking, but I don't hear you. I'm sorry. I give you some time to figure it out. If not, but we are also, yeah, I heard some sound.
Okay, so
Yes.
It doesn't work with my headphones plugged in.
No, no
All right.
worries.
It depends whether you're coming from the sides or from the top. Like if you're coming from above, it's smaller because you have like less time in which you are on the button while you're dragging your cursor over it.
Yeah, that's good. So unfortunately, you're a good student. So my next slides will be kind of obsolete, because then I would give you like, hey, what if we come from these stones here? And then yes, you will see that, for example, if I come from the 1, the width of the button is this one here. If I come from 2, the width of the button is this one. And if I come from a diagonal direction, it's this one. So it's actually kind of the trajectory from where we come slicing through the button. That's the width that we will have in Fitz law. And this was actually found out by McKinley and Buxton in 1902. Something what's actually interesting in Fitz law is that also there are very good positions. Well, let's say, let's go to another slide. Where is it? Where's the slide where we talk about the perfect positions of something like this? Hello. So here's where this iPad thingy is not really working out for me. I want to have this slide because I think it's better if I show you this beforehand before I show you something else, and you know the spoiler here. Okay, so based on this, if I want to have a button on my interface here, so let's say a regular button like this here. Do you have some suggestions where I can put this button to make it as easy as possible for the user to hit, or to make the time the user takes to hit this button as small as possible? If you saw it previously, then you need to argue for me why this is the case. Okay, yeah, I see people raising their hands. So I think the first one was Sansilla.
I think on the right-hand corner below the screen, it will be easier for user to tap it because most of the people are right-handed, as we can assume.
So you mean here? Or here?
Just the bottom of the right-hand corner.
Bottom of the right-hand corner. So you mean this one here?
Yeah.
Okay, and you say it's good because people are usually right-handed, so they move down here. Yes?
Yes.
Okay. Other ideas? So first of all, thanks. Other ideas. Next, Mateus.
The first question that we need to ask is what we want this button to do. If it's a button that we want to click often, then I think central position is nice. If you, but if this is, for instance, a close window button, then we want this button to be out of the way.
Interesting. Actually, my arguments are not depending on what the button do, but your arguments are not wrong, I would say. So yes, if we include what the button does, these are arguments that you can make. But let's assume it doesn't matter what the button does. Just let's think about, I would also write this again, just think about Fitz law. Okay, if you just keep Fitz law in mind. Damn it, I look to the side and now I don't remember anymore who raised their hand first. So I will go from left to right how I see it on my screen. So Elena. Who lowered the hand? So Fabian.
No, sorry.
No, it's fine. Elena, yes.
Okay, I wanted to say that the button should be near the position of the mouse where it started. So
yes.
I don't have to move it as much. And maybe the button should be as big as possible. That makes sense.
Sure. So first of all, the first thing that you suggest is just put it here, basically. Yes. Well, that's actually pretty good because with this, we minimize the distance as much as possible. So you don't actually have to move. So the distance will be 0 and the whole thing will be 0. So yes, this is one of the optimal things. Making the button bigger at this situation does not change a lot. If we put it anywhere, yes, a bigger button would also, oops, spoiler there, would also make it better there. Okay, then since I spoiled it for you already, let me introduce another concept here. So, or does anyone have an actually really nice idea of the people that still have raised their hand that I want to share?
I had the idea of picking the corners because this way you're making the white like infinitely large because you can just fling the cursor to the borders. So if you're taking the corners, but only if you take the corners, if you're taking like only the border in the middle, it does not really work because you can like overshoot to the left or to the right.
Right. So I'm thinking about whether you already took the course or already read ahead, because yes, this is absolutely right. So actually there's a nice, let's call it hack in Fitz law, that if you put things at corners or at positions on the top like this, and your mouse cursor comes from here and goes to here, actually we cannot overshoot the target anymore. So what you can assume then, and that's the nice hack, is that the target is basically infinitely large because we can just approach it with as much speed that we can manage to do with our hand. And we do not need to worry about overshooting the target anymore. So, and therefore, Fitz law gets really interesting there. So we can just assume that that the width of the thing is then infinitely large. What you also said correctly is that if you put it on the sides here, what happens that you can sometimes test this with your computer. If you fling your mouse here, interestingly, the moment you hit this here, usually your mouse goes like there or there, and then it doesn't work anymore. If you put these in the corner, then your mouse actually always hits the target. Yeah, I see the what is, if you have a second monitor on the right or top, yes, then of course, at the moment you can overshoot these. So if you, for example, have a second monitor on your right side, then yes, this does not work anymore. So it only works if your cursor stops at this position. I saw some questions coming up. So Fabian, do you have a question or a suggestion?
No, I just wanted to add that, first of all, can you hear me?
Yes.
Okay, perfect. First of all, I wanted to add that the top or the sides might actually also work if the buttons or the detection is just very wide. Yes. For example, the whole Windows arrow snap, I think, works pretty good, but only because pretty much the whole top or the whole side of the screen does exactly the same thing. So the movement to the side from the mouse, which is a little bit annoying, doesn't really matter in this case. So
right.
Probably if the function is just for the whole side, it's probably still usable. And also maybe distinctively has a distinct function from the corners.
Yeah, I mean, you can basically see this, I think, on Windows, when you have your taskbar on the bottom, not always visible, you can just flick your mouse downwards to the bottom of the screen, and then the taskbar comes up immediately. And you don't need to think where it actually is, you just need to fling it downwards. Okay, people lowered their hands. Suraj, I hope I pronounced this correctly. You still have a question?
Why not just click anywhere on the screen?
Why not click anywhere on the screen? What do you mean?
Like the right click option that you have on the cursor, for instance.
Yes,
so
the right click option.
Location for a target that's really important could be anywhere. So just make it so that the whole panel is the target.
Right. Yeah. This is basically what was suggested here. So kind of put an invisible button below of the mouse cursor. And this is what basically was all your context menus do. So whenever we click anywhere with our right click on the screen, a context menu opens immediately. And this is mostly at the position where we want to have it, to click it as fast as possible. So yes, we can the right click is always the button which is below our cursor again. Okay, then I have questions by Victor or Malik. Let's say Victor first.
Yeah, I would like to ask a question. If we don't have these borders like torso space, when we have right part is linked to the left one, yes. Like as you're playing Snake, for instance.
Yes.
Is the best position is in center for this case, or which one?
If you want to optimize Fitz law, then yes. If you don't have this infinite width anymore, I mean, then you can also make the button then infinitely large or something like this. But yeah, let's say the correct position then is always there where the mouse cursor is. Yes.
Okay, thanks.
Sure, Malik.
Yeah, hi. First of all, are we talking about designing for desktop or also for mobile and so on?
This is designing for a desktop. The moment touchscreens are involved, things get weird again, because with a touchscreen, for example, your finger can overshoot on the side of the screen. Fingers behave a little bit different than mouse cursors. So Fitz law wasn't even initially designed for desktop. As I said, it was designed for real world scenarios where people actually click buttons. So even just applying it to a desktop already is not the thing that Fitz had in mind afterwards. Or previously, but actually we found out that it works. And Fitz law is actually a really robust formula that, we have shown, or other researchers have shown quite a lot, that you can also adapt it to different scenarios and everything. The problem that I have, a look at the time, I see a lot of your questions coming up. We only have 45 minutes left. What I would say now is I will continue with the lecture. If you still have the questions, I will stay in here afterwards a little bit and you can discuss this later with me. So since we discussed this now, let's go back to the part where I was previously here, because this was basically us showing you that, yes, we have these things already also in real life scenarios where, for example, showed you the taskbar on the bottom here, where you can hit these targets. For example, this button here is at the perfect position. So whenever you want to open your Windows menu, you just need to flick your mouse down here, press this button, then the menu opens and you are immediately there. You have a similar thing on macOS where basically the taskbar is not on the bottom, but on the top here. And here you basically have this apple on top here that you can usually click, which button is larger than just the apple. So you can also just fling it in here and also sometimes have the same here. Okay, so then another thing that we have is improvements of its formula. As I said, basically HCR research picked up this formula and we looked at it and saw that it's quite robust, but it also had some difficulties. So let's look at this. So here we have the graph with Fitz law. What you can see here is Fitz law for a certain distance and a certain width. And if you just look at this graph, can you see a problem here already? Malik, is this still a question or are you answering? Can you answer this? Because you still have your hand raised? Okay, not anymore.
Sorry, I forgot.
No problem, no worries. Okay, does somebody has an idea what can be a problem with Fitz law? If you look at things, or if you basically look at values for D and W, with which values can we have problems here? Yes, Mikkel?
If the button is far wider than the distance to our current position, we have a negative value at the time we need.
Yes.
And that might be unrealistic.
Yes, because with negative time, we don't really know what it is. So we don't know whether we are traveling back in time, whether we are, I don't know. It's weird. So we cannot have negative time here. So yes, the moment you have something like this, so you have a really large button, and your cursor starts here. So the distance to the button is not really large. Fitz law doesn't work anymore. And this is something that actually was also found out by other researchers, for example, first Welford, and he tried to fix this by just adding this constant factor of 1.5, and he also got rid of the 2 here, so there's no 2 anymore, and we just have 1.5. And there he already shifted this kind of a little bit to the left, and he got rid of most of the problems. Interestingly, not of all of them, we still have these values here that can become negative. So afterwards, we have another formula, which is Shannon's formulation. And Shannon kind of shifted it again with just a simple +1 here. So we have a +1 here now, and this basically gets rid of all the problems. He also introduced some different things. So he also introduced these 2 constants here, or these 2 values, A and B. What these are is basically when we have our goal in mind that we want to use Fitz law to kind of simulate devices. Some devices behave different. So we kind of sometimes need to adapt Fitz law. For example, let's say we started with our mouse. Usually I have my hand on my mouse and I can immediately go to the button. If let's say I have this pen here that I'm constantly using and I want to tap something, I might, for example, first of all have this pen usually in my hand, and then I need to go to the screen. So I might have a constant factor here that's a little bit different to the mouse. So my pen might behave a little bit differently than my mouse. So what we can actually do, we do what we did before. We give some users a pen, let them do a tapping task a lot of times, and then afterwards look at the curve that we have there and then fit the curve correctly into this by kind of looking at these A and B values. So if we have a constant factor in there, we can shift the graph up and down by adding a constant with A. And if the slope of the curve is a little bit differently, we can work out a new slope with this B factor. And usually what we do, what you can see here, we usually use A with 0 and B with 100 milliseconds to have some rough estimates beforehand. So this is what we will usually do for some examples that we will do, but we will then give you these values. Okay, so let's do an exercise like this. So we have these values here. So how much faster does calling become by moving the call button, so this button here, from 17 millimeter distance to 30 millimeter distance, measured from the middle of the keypad. The size of the call button is 10 by 10 millimeters. And we will use Shannon's formulation with this. And as I already told you, we do A is equal to 0 and B is equal to 100 milliseconds. And I would say I will give you some minutes to figure this out yourself. So you have the formula here, you have the values down here and all the other values here. And let's say I will give you, how much time do we have? Yeah, let's do 4 minutes. And I see you big in 4 minutes. Okay, then let's see whether I calculate this correctly. So we have 2 distances here. So let's call this one 1 and this one 2. So we want to have the distance of 1 minus the distance of 2. Okay, let's make this a little bit larger. Okay, so what we have in mind again is that we have the formula down here. So A and B are constant. So let's calculate T1 first. So T1 is equal to A plus B times the logarithm of the base of 2 divided of D divided by W plus 1. So let's put in these numbers here. So let's say A and B, leave them as they are for ones, and we have the logarithm of the base of 2 to the distance. The different distance of 1, as we said, is 70. And now the width is interesting. We're coming from down here. So basically our fingers go from here to the center here. So kind of this direction, not squiggly, directly. And so the width is the one that we are traversing here, this width, and we said that this thing is 10 by 10 millimeter. So our width here is 10 millimeter. I hope this was understandable. So we have 70 divided by 10 plus 1. And this then again is A plus B times the logarithm of the base of 2 And 17 divided by 10 is 7, if I still understand correctly, plus 1 is 8 then. So we have the logarithm of to the base of 2 of 8, which then should be a plus b times the logarithm to the base of 2 from 8. And this one here is basically what you always, when you're in the exam scenario, because usually we do these that you don't need to have a calculator with you. So it's basically what's basically 2 to the power of what is equal to 8. And this, of course, is 3 here then. So we have a plus b times 3. Okay, so this was the first one. And then the second one, T2, I try to be a little bit fast here, is a plus b times the logarithm of 2. Now we have different values here. We basically have 30, divided by 10 plus 1. And this here is 30 divided by 10 is 3 plus 1 is 4. So we have a plus b times the logarithm to the base of 2 of 4. And again, what I always do is I ask myself 2 to the power of what is equal to 4, and that's 2. So we have a plus b times 2. Okay. And then again, we can also calculate these now, but we know that the a is basically 0, so we can just omit a always, and then we had t1 minus t2. So t1 minus t2 is equal to b times 3 times can come back to me, b times 3 minus b times 2, and that is b times 3 minus 2, which is 1. So it's basically just b. So the difference is 100 milliseconds. Okay. Also, you don't need to do it like this. You can also calculate both numbers first and then divide them out, then subtract them afterwards. You don't need to do it as I did it. How we come to these numbers is basically usually always the same. But as we said, we usually do these numbers in a way that you don't need a calculator for them. So usually if you have weird numbers, something somewhere is wrong. Okay, so let's go back to the slides. So this is also the solution here. And as you can see correctly, we find out it's 100 milliseconds. Yay.
This content was provided by RWTH Aachen University.